This is a Raspberry Pi Pico Plus FPGA PCB project featuring the RP2040 dual-core microcontroller and Intel/Altera Cyclone 10 FPGA to experiment with different communication schemes between the microcontroller and the FPGA. It has plenty of onboard peripherals to make it more fun to play with. Things like push buttons, LEDs, dip switches, an IMU sensor, NeoPixel RGB, analog RGB, an OLED display with a backside connector, potentiometer, an EEPROM memory chip, and USB ports for programming and serial communication. On this board, we can set things up in such a way that the FPGA is fully transparent from the point of view of the microcontroller, and it acts like a memory mapped I/O peripherals extension, so we can build some custom peripherals on the FPGA and use it by the microcontroller just like any built-in peripherals on the MCU chip itself. Or the other way around, we can set up a soft-core processor on the FPGA side and configure the RP2040 as a slave device. It's so flexible with endless applications possibilities. This video project is sponsored by NextPCB. A huge thanks to NextPCB for making it possible to do this. As you can probably tell, it turned out to be great. The build quality and pricing of these boards is absolutely amazing. More on NextPCB later in the video. Let's waste no more time and jump in to discuss the architecture and hardware design of this project. We will also develop some firmware in C and HDL code in Verilog to bring up our board on both sides, the RP2040 and the FPGA. And here is how this system is supposed to work at the end. On the very low level, there is a SPI bus between the microcontroller and the FPGA, connecting both chips together. On the RP2040 side, we will use the SPI driver from the C SDK, and we will implement this software stack to implement some sort of MMIO addressing, IO operations, read and write, and so on. This will be in this manager layer to abstract the MMIO peripherals addressing at the FPGA side from the above layers. On top of that, we will implement some firmware device drivers for the MMIO peripherals. If we have, let's say, UART here, or input capture unit, ICU, or PWM on the MMIO peripherals implemented here in hardware, we will need to implement some device drivers for these peripherals to abstract away the internal operations of these peripherals from the application layer. So we can use, from the point of view of the application, we can use a UART peripheral built in on the microcontroller itself, or we can use a UART module that is implemented in hardware on the FPGA side. This is the basic idea behind this software stack. And now moving on to the FPGA side, this FPGA chip is a low-cost part. It costs like 5 USDs, and it has 6K logic elements, which is enough to build a lot of things. But what we are going to do is we will implement an SPI slave device to receive the SPI messages from the microcontroller, and we will implement some sort of logic and state machines to decode the messages coming from the or the decoded messages for the MMIO addressing done at the microcontroller's side. Then we will need an MMIO controller to standardize the way of connecting these peripherals or the custom peripherals that we will build on the FPGA side to make these connections standard, and by doing this we make the system more portable and easily extendable. And this is the overall picture of what we are going to do, but of course there are some things that there is no room to discuss in this video, so I will make it maybe later. There is actually another bus other than this SPI bus between the microcontroller and the FPGA using the PIO state machines in the RP2040. There is a 4-wire bus connecting the FPGA and the microcontroller, so we can implement any custom digital communication protocol to achieve very high-speed data transfers, which leaves the door open for more possibilities and experimentations in the future. And maybe we can also make this into AXI4 or AXI Lite bus, so we can connect any standard IPs or soft-core processors on the FPGA side. And let's now jump to our project article. I will leave a link to this article in the description of this video. It's a pretty long read, but it documents everything in this project that we will discuss today. And this is the top level hardware software architecture that we have discussed earlier. And now let's move to the hardware design guidelines and documents that I used to build this PCB. For the RP2040 side, it's exactly like this previous project that I have discussed in a previous video, using the exact same schematic and components, but I have just rearranged the components to fit on my new PCB. Regarding the FPGA side, I have used these documentations and guidelines from Intel for the Cyclone 10 FPGA device family. This is the datasheet of the device, and this is the device design guidelines. This is the hardware design guidelines and checklist. For the pin connections, the configurations, the voltages, and the power supplies. And by checking these checklist items, you will make sure that you have considered everything that is needed to have your FPGA chip laid out and connected correctly. And that is what I have done here. This board is actually smaller than what it looks in the CAD tool. It's 6 centimeters by 9 centimeters. Those are the power supplies needed by the FPGA. 3.3 volts and 2.5 auxiliary power supply and 1.2 voltage core supply for the FPGA chip. This board can actually be powered from any of these USB ports. This is the power supply section for all of the supplies needed, and there is also an analog voltage reference for the RP2040's ADC to give it more chance of giving some stable readings. The RP2040 chip, as we have seen in a previous project, uses a protocol called XIP, or execute in place, to connect the external flash memory, and that's what I have done here. I have also connected the OLED display to the microcontroller. The IMU sensor is also connected to the RP2040, and this rotary potentiometer is also connected to the RP2040. This is a reset button and boot for the RP2040, and this is a test LED also going to the RP2040. Moving to the Cyclone 10 FPGA, as we have seen, these are the required power supplies for the FPGA. This is a 50 megahertz CMOS oscillator feeding the clock input of the FPGA. It has multiple clock inputs, but I'm using one of the primary sources. All of these dip switches LEDs are going to the FPGA. This new pixel RGB and this analog RGB, JTAG connector, push buttons, all of which are going to the FPGA chip, and also the done LED that indicates that the FPGA has fully completed the configuration process. As you probably know, any FPGA chip, when it gets powered up for the first time, every time it's just blank. It's just configurable logic blocks that are doing nothing, and it loads in the bitstream file to configure the configurable logic blocks according to your digital design, so that of course when we first power up our FPGA, it won't have any of these. It will be just blank. It will do just nothing, and it will stay there transparent, and it won't affect the microcontroller in any way until we program the FPGA to do something. And of course, when it first boots up to load the bitstream, it uses the mode selection pins. There are 3 pins for the mode selection that dictates how this FPGA chip will load the bitstream file. I have selected this mode, which is active serial, to make the FPGA chip load the configurations or the bitstream from the onboard SPI flash memory, which is located here on the backside. This is the flash memory that goes to the FPGA to store the bitstream files. But of course, we can always use the JTAG connector. It's the primary source of loading bitstream files. However, if you load some bitstream over the JTAG to the FPGA and you click this reset button, it will get wiped out and it will be replaced with whatever is loaded on the SPI flash chip. So if we need our bitstream file to be permanently saved, we need to write it to the SPI flash memory chip. And we will see how to do this later in the video. I believe this is everything about it. I have also created this pinout diagram as part of the project documentation to make it more easy for myself to use this dev board actually. Everything in blue is going to the FPGA, and everything in green is the RP2040 signals. Like the OLED display, these IO pins, the potentiometer is analog channel number 0. This indicator LED is GPIO 22 of the microcontroller, which we are going to test very soon. And those are the communication buses between the FPGA and the microcontroller. This is the SPI bus, and this is another 4-wire bus that connects the microcontroller and the FPGA to test using the PIO state machines of the microcontroller to create some custom communication protocols with the FPGA. And at this point, it's time to go to fabrication and send our board Gerber files to start the fabrication process, and it's our sponsor time. I have used NextPCB service for this project. They have a lot of services to use, starting from the PCB prototypes that starts at 5 USDs for 5 boards. By creating a new account, you will be eligible for this discount coupon. And as you can see, a 2-layer board, 10 centimeters by 10 centimeters, 5 boards will cost you like $5 only. If you are going to use any of these chips, there is an accelerator program at NextPCB that will give you some more discounts for using the RP2040 or RP2350 chips on your board. You will get free PCB assembly service for your project if you are using any of these chips. So I think you should also check it out. While using NextPCB service, you will also need to check out the HQ Online, which is their main parts sourcing company that you can use to source your parts. I have managed to get these parts for my board at very reasonable prices. The RP2040 was $1. This is a $5 part. The FPGA, the power supply ICs, the sensors, everything is just offered at competitive prices. Regarding the stock of these parts, let's consider this microcontroller chip. You always want to use the chip immediately. If you always want to use the manufacturer part number of the chips that are already in their stock. However, if you didn't find any of your needed parts like this, and it requires like 4 to 7 working days or 3 to 5 working days, it's absolutely fine. You can always use it, and it won't take that much actually. According to my experience, I have used a lot of parts that were not in stock, and it took a lot less time than the announced 3 to 5 working days or whatever. So just keep that in mind. In KiCAD plugins, you will also find a plugin to export the fabrication files in the format that the NextPCB system recognizes. So you can install this plugin and export your project with a click of a button and upload it to the NextPCB website. After uploading my Gerber files and selecting the fabrication options, I have also uploaded the BOM file and the component positions file, and the system has recognized the parts that I am using in my design. The matching was successful. I was able to pay for the order and wait for the delivery, and here is my board after receiving it from NextPCB. And now let's get to the fun part and start testing our board. Here is what I needed to do in the first time to assemble my board by hand. These parts require manual assembly, like the OLED display, the potentiometer, the dip switches, and all of the pin headers. I gave it a quick inspection using the microscope with a fine needle and digital multimeter probe to check up on any critical short circuit path and the continuity of critical power paths like the VCC, VCC internal, VCC auxiliary, etc. Everything looked perfect to me at that point, so the next step was to power up my board using a current limited power supply with 5 volts, 50 milliamps, just in case anything goes wrong. And thankfully nothing was wrong, and my board just drew in like a couple of milliamps. Then I moved on to check the power supplies and measure the voltages. I started with the digital 3.3 volts supply, 1.2 volt core voltage for the FPGA, and the 2.5 volts auxiliary supply, and finally the 3.3 analog reference voltage, which was spot on, and I was confident enough to plug in the USB and start doing some real work and uploading firmware to the microcontroller. And we will start our bring up testing with the RP2040. We will do some basic LED blinking for this onboard LED that connects to the RP2040 pin number 22. So I will go to the VS Code. I have shown you actually the steps to create and build firmware for your custom RP2040 board using the CSDK and Arduino in the previous project video if you want to check it out. But now I am going to skip forward this step. I will build my project. I'm just toggling on and off this LED pin, which is pin number 22, and the build is successful. And here is what I'm going to do. I will connect this RP2040 USB to my PC. To flash our firmware, what I'm going to do is to hold this boot button and keep holding the boot button and hit the reset button once. And here is our RP2040 USB device. I will go to the project build, and this is the UF2 file. I will drag and drop it here on the device. It will restart, and as you can see, the microcontroller is blinking the LED. This is the first live test for the RP2040, and thankfully it went successful. And moving on to the next test, we will test the ADC with PWM. So what we are going to do is read this ADC channel that goes to the potentiometer, which is ADC channel number 0, and use that ADC reading to control the PWM output on that LED. So this is our next test. And this is the code for this example. We have an ADC pin, which is 26, PWM pin, which is the LED's pin 22. We first initialize the ADC pin, and we will initialize the PWM output pin, and we will read the ADC into this variable and set this value as a duty cycle for the PWM output. That's all about it. I will build this project, and we will also do the same. I will keep the USB port going to my PC, and I will hold the boot button and click the reset button once. So there we go, and I will drag and drop the UF2 file. As you can see, I'm controlling the PWM output on the LED using the onboard rotary potentiometer. We will stop at this point after making sure that the RP2040 microcontroller is running okay. We need to make sure that the FPGA side is also alive. So the first live test for the FPGA is to use these push buttons to light up the analog RGB. We will connect the switch number 2, 3, 4 to the red, green, blue of the LED diodes, and we will also connect the dip switches, the 8 dip switches, to the 8 LEDs on the board. This is the first basic test that we can do to make sure that the FPGA is also working fine. Let's open up Quartz Prime. We can make a new project, or we can use the project that I have created for this test. So I will not use this new project. I will open a project, which is this one. By the way, this is the latest version of Quartz Prime Lite edition, and this is the top file of the hierarchy for this project. Actually, we don't need anything other than this file. Here I'm defining 8 wires for the LED, 8 inputs for the dip switches, the 3 push buttons, 2, 3, and 4, and 3 wires to connect the RGB LED. And as you can see, I am just writing or assigning directly the digital value of the button to the corresponding LED diode for the RGB, and for the dip switches I am assigning the 8 values of the dip switches to the 8 wires of the LEDs. That's all about it. We just need to tell the synthesis tool which pin is which. As you can see here in this pinout diagram, these are the FPGA I/O pins for these dip switches, and those are the LEDs, those are the switches or the push buttons, and the 3 pins that connects the RGB are as shown here. So I will show you how this is done in Quartz Prime. We go to the assignments and pin planner. This is a graphical view for our chip, and here is our signals in the design. In order for this to appear in the pin planner, we need to build it once at least. I have done that earlier, that's why these signals are appearing here. And here is how you connect it. We go to the pinout diagram, we pick up any signal. Let's say this switch number 3 connects to the I/O number 136. We go to Quartz, and here is the switch number 3 or button 3, and it connects to the pin number 136. You also can select the I/O standard for these I/O pins. There are a lot of I/O standards for the I/O pins, but on my board all of the I/O banks of the FPGA are connected to the 3.3 volts rail, so that is the standard I'm going to use in my design. You can also choose the current drive strength, the slew rate for your I/O pins, and this is mainly how you assign the physical pins to the signals in your design. Any changes you do here will reflect in the assignments and assign editor, and this assignment editor is a non-graphical way of doing exactly the same as what we have done in the pen planner tool. I will close it. I have completed the synthesis of this project, so here is the completion report. As you can see, I'm not using any logic element of my device. The consumption is 0. However, I'm using 22 pins or physical I/O pins. Now we need to send this bit stream or the output bit stream file to the FPGA. Here is how we are going to do it. For the first time, we are going to use the, actually most of the time we don't have a USB flashing method for this FPGA on this board. We only use the JTAG connection. So I will connect the JTAG to a USB blaster. In the market, there are 2 USB blasters that you will find for Intel FPGAs. This one on the left is the most common. You will find it everywhere. It costs only 1 USD as far as I know. I have one of these. I've used this USB blaster for old CBLDs and FPGA families from Intel back in the days. And this is a more recent version of the USB blaster from Waveshare, and it costs like 40 USDs. It's a more expensive and recent version of the USB blaster. And in my case, using the newest version of Quartz Prime, this USB blaster is not recognized in the software at all. The PC device manager does recognize this USB blaster. The device drivers are installed correctly, but it doesn't get picked up in the Quartz Prime software. On the other side, this USB blaster works like a charm, and that is what I'm going to use in our project. Now I have hooked up the USB blaster to my JTAG connector. We need to have our board powered up using any of these USB ports. So I will keep the USB cable going to this port, and I will connect the JTAG to my PC. And it's now connected. Let's go to the tools and select programmer. And as you can see, the configurations or the bit stream is going from the JTAG over the TDI pin to the FPGA chip. This is what we are going to do. Double click the file. This is the output SOF bitstream file. I will click open and check this program and configure, and will make sure that my hardware is detected. It's now not detected, no hardware. So I will click on this hardware setup, open this, click my USB blaster. I will click close, and it's now connected in JTAG mode. Everything looks fine. I will click on this start button. It will start sending the bit stream. It is completed successfully. The push buttons are controlling the RGB LED, and the dip switches are controlling the corresponding LEDs. Everything looks fine as we expected to be. However, at the end of this test, if we click on the reset button, everything gets wiped out, and we expect the first and last LED to be turned on. However, they are not on. They don't respond to the dip switches states. This is because the bitstream file that we have sent over JTAG, it gets wiped out when we click on the reset button. So we need our design to reside permanently on the flash memory chip of the board. We will head back over to our Quartz Prime project. We will click on the file and convert programming files. Using this tool, we will convert the bitstream SOF file into a JTAG indirect configuration file that resides on the SPI flash chip. Here is how we do it. Here we will select the JTAG indirect configuration file format. Then we will select the configuration device. Device family is Cyclone 10 LP. Active serial mode. Okay, and we will select the ECPQ64. This is the memory chip I'm using on my board. Now this is fine. Then we need to select the flash loader device. We will select add device, Cyclone 10 LP, Cyclone 10006. This is my chip. I will select it, and in the SOF data we will add this output file that we have just sent over the JTAG. We will click generate, and the JTAG indirect configuration file is successfully created. We will close this and go back to the programmer tool. But as you can see, it is configured in the previous way, so that the FPGA gets the configurations from the JTAG, and there is no flash chip. So I will remove this by clicking on the delete button, and I will add file, and this is the JTAG indirect configuration file that we have just created. I will click on open, and as you can see now, the configurations are coming from the JTAG and they are going to the memory chip, and in this way the FPGA will permanently save the bitstream file on the flash memory chip, and when it gets reset, it will load the bitstream file from the SPI flash memory. I will check this program or configure option, and I will click on the start button. It will now configure the FPGA and flash the bitstream file to the SPI flash chip. It will take a bit of time, as you can see, and now it is completed successfully. Let's test our FPGA project again. Everything works as expected. The push buttons, the RGB LED, the dip switches, and the LEDs. And this time, when we do a hardware reset for the FPGA, it will load the bitstream file from the SPI flash. The first and last LEDs are behaving as expected in this time. And now we have made sure that our FPGA chip is alive and it's working as expected. The push buttons, the LEDs, the JTAG connection, the SPI flash configuration, everything is working as expected. Now we will move to the real test. This is the first test and the core test actually of this project. We wanted to communicate between the RP2040 and the FPGA. This is the test that we are going to conduct right now. Let me get back to the first anticipated architecture. Of course, I don't have the time to build all of these software and hardware stacks. So what I'm going to do is to discard all of these things. I will just use the SPI driver from the C SDK of the RP2040, and I will also remove all of these parts. I will keep the SPI slave device, so we have a communication between two SPI devices, the hardware SPI on the RP2040 and this SPI slave device that we will create in Verilog. I will also make a PWM module to generate a PWM signal to an output LED, and use the RP2040's ADC to read the potentiometer, and use the potentiometer to control the output LED. This is basically what we are going to do in this next project. As you can see on the RP2040 side, I am reading the potentiometer value using the ADC and sending the 8-bit value. I'm scaling down the reading to 8-bit and send the 8-bit value to the SPI, which sends it to the SPI slave device that we will create on the FPGA side, and the received byte will be sent to a PWM generator as a duty cycle value. The duty cycle value will update the PWM generator, which controls the blue LED of the RGB LED. This is not a proper SPI communication test. However, it's very visual. Any wrong bit in the communication between the SPI devices will result in a flickering in the LED. The PWM duty cycle will change in a very insane way, and we can pick this up visually, or by using an oscilloscope. We can easily check if the SPI communication is going on properly or there is anything wrong. However, if we want, and that's what I'm going to do next, is to create a more reliable test bench using CRC checking and such, to send some big chunks of data from the RP2040 to the FPGA and make sure that the CRC is matched. But for now, this test setup is sufficient, and if we couldn't get this to work actually, all of this and everything will be just sweet dreams. If we couldn't get the SPI communication between the RP2040 and the FPGA up and running properly, we won't be able to build up on that and make anything that we anticipated at the beginning of this project. So it's very critical to perform this test and to get it passed successfully. And let's start with the C code for the RP2040, which will read the ADC channel connected to the potentiometer, channel number 0, scale down the reading from 12 bits to 8 bits, and send the 8-bit value over SPI to the FPGA chip. We will initialize the ADC channel and the SPI communication, and we read the ADC value, scale it down to 8 bits, and then we send the 8-bit value over SPI, and that's all about it. We flash this code to the microcontroller, and now we will head over to Quartz to create the SPI slave device, PWM generator modules, and assign the physical constraints for the I/O pins of the FPGA. And here we go. Of course, this time the project is a bit more complicated, as it has a lot of signals. We are using the onboard clock, the 50 megahertz clock oscillator, and we have those are the same connections as the previous test. However, now we have 4 more I/O pins for the SPI bus: the MISO, MOSI, chip select, and the SPI clock line. I'm not going to bore you with the details of this project this time, but I'm just instantiating a SPI slave device, which is in a dedicated Verilog file, and another file for the PWM generator, which is also instantiated here. And this code actually does what is shown here: the instantiation of a SPI slave device, instantiation of a PWM generator, and the SPI reception done signal is used to update or latch in the received data into the duty cycle control register of the PWM generator. And we will set the SPI communication speed to 1 megabit per second on the RP2040 side, and then we will pump up the speed gradually to see what is the limit that we can achieve in terms of speed of SPI communication between the RP2040 and the FPGA. We will start the synthesis tool, and this time we are using 1% of the logic capacity of the FPGA chip, some I/O pins, and one of the 2 PLL units on the FPGA. We will talk about it later. And now let's write the bitstream file to the FPGA and start the test. And thankfully the test went successful. As you can actually see, the potentiometer reading of the RP2040 is sent over SPI to the FPGA, and it's updating or controlling the duty cycle of the PWM generator implemented on the FPGA side. And as we can see, the blue LED over the RGB, which is an indicator of success. Of course, I have used another I/O pin, as you can see here in my project, for the PWM, to check the PWM signal on one of the I/O pins on my board using an oscilloscope to make sure that the PWM signal is not flickering, there is no jitter, there is no any weird stuff going on, because if one bit is received in an incorrect way, the PWM duty cycle will be messed up, and the signals or the waveform will be very noisy and jittery, and we can easily spot on the failure. At that point, I went over to the RP2040 code to start increasing the SPI communication speed gradually up to the point where it was, I believe it was, yes, it was 30 megabits. At 30 megabits per second, the communication started to fail and started to see the flickering on the LED that I told you about. At that point, I was using the raw 50 megahertz clock source for the FPGA. And at that point, we need to increase the clock of the logic of the SPI peripheral that we have created on the FPGA side, so it can respond and interact with the fast signals coming from the RP2040 at 30 megabit per second. The 50 megahertz clock was not enough, so I used one of the 2 PLL units on the FPGA. As you can see here in Quartus Prime, there is a tool here in the basic functions, clock and PLL. Yes, this tool to create a PLL instance, which is my PLL, and you can configure this PLL tool actually to generate whatever clock you want using the onboard clock. I have connected my 50 megahertz clock input and configured the PLL unit to generate 300 megahertz clock output, and I have used that 300 megahertz clock output from the PLL to clock or feed in my SPI interface instance, and also the PWM generator. The PLL performance of this FPGA chip actually can be checked out here in this data sheet of this device. Here, yes, in this PLL specs, here is my FPGA port, My speed grade is C8, so the PLL can output up to 400 megahertz clock. This is the maximum limit that I can reach using this chip. However, I don't need that much of speed. At 300 megahertz, it was more than enough for me to achieve the maximum allowed speed for the RP2040 itself. The RP2040 SPI can reach up to 62.5 megabit per second using the default clock configurations in the C SDK, which is 125 megahertz for the system clock and half of that clock to the SPI. Finally, I have set the RP2040 SPI speed to the maximum limit and rerun the test again, and it was successful. And this was definitely good to see, given that I'm not using any inline or parallel termination resistors for the SPI lines or whatever. The board I have designed here is just a 4-layer stack up, signal, ground, signal. The connections between the RP2040 and the FPGA are very short, point-to-point connections. Nothing was special about routing the SPI lines. So it was very good to see this performance at that point. And after passing this test, which was fundamental in my project case, to have a SPI communication properly working between the RP2040 and the FPGA, it was more a relief. Anything past that point was a quick win for me, just like operating the OLED display or whatever. So I went over to test the OLED display in the next project, as you can see. And in this demo, I'm showing the Raspberry Pi Pico logo, my logo. Tell me if you recognize this. An image of the board itself, and some NextPCB digits, which looks very amazing on this OLED display. And that's all about it. Given that this is the first iteration of this project, this is very successful actually. There are some secondary peripherals on the board that I didn't have the time to test or to write firmware drivers to operate these devices, like the IMU sensor, the EEPROM memory, or the NeoPixel RGB LED. However, I'm pretty sure that they will work just as fine. What about the next steps? First of all, I want to increase the SPI communication between the RP2040 and the FPGA to see what is the fundamental limit that we can reach. The first step to do this is actually to update my Pico SDK, CSDK, to the new version. The new version has an overclocking for the RP2040 fully supported in the SDK itself, which goes up to 200 megahertz, and I have seen some people online pumping up the clock even beyond that limit. But first of all, let me test the 200 megahertz clock. Then maybe I will move to test the custom 4-wire bus that I have made between the RP2040 and the FPGA using the PIO state machines to achieve maybe higher data transfer rates. This is one thing to work on. I just also wanted to let you know that I'm aware of this open loader FPGA project, which supports a lot of boards or FPGA parts. However, my part is not one of them. If we go to the Intel Cyclone 10, yes, this is the only part supported by the open loader FPGA. I'm saying this because I know a lot of people will maybe write to me in the comments that we can use the RP2040 to program the FPGA or load some bitstream files to the FPGA. I believe this is an interesting thing to look for maybe in the future. And if we look up the cable compatibility with the open loader FPGA and check these cables, we will find the DirtyJTAG project. The DirtyJTAG actually is an implementation for, or a simple implementation for the JTAG protocol using these microcontrollers, the STM32, the Bluebell, and the Raspberry Pi Pico, which we could have done. We could have used the RP2040 as a DirtyJTAG device to program one of these FPGA devices, which would be an interesting idea to look up to in the future. And that concludes our project video. I hope this was helpful or inspiring for you. Let me know if you want to see something specific in the future, and I will catch you in the next one.